All right, calculus fans. Hey, this is Mr. MathWell here, and it is almost 5 o'clock on Friday, and I don't know why I'm still at school. Anyways, I just got so excited about this example, and I had to make a video here just to show you. So, what I'm going to do is I'm going to compare for you the DI method, okay, integrating by parts, the DI method, versus the integrating by decomposing the integrand into partial fractions, okay? So it's a big battle here. It's DI versus partial fractions. Okay, so I'm just going to do both ways, and you can judge for yourself which one you like better. I think the DI method probably is going to be a little more straightforward. But because we're learning partial fractions, I thought I would just do one example where you could do both. All right, are you ready for this? So the DI method is going to be over here first. And again, what you want to do is you want to, you're going to do this little chart, DI, and you're going to do plus, minus on the side. And what we're going to do is we're going to split this integrand here into two parts. And it's going to be x plus 5 times 1 over x plus 3 all squared, right? And so I want to choose one of these to differentiate and one of those to integrate. And that's what we're going to do. So I'm just going to leave this off to the side here for right now. Actually, I'm going to get rid of that so I can have more space. Do that later. Anyway, so what I'm going to do is I'm going to choose x plus 5 to differentiate. I'm going to choose x plus 3 to the negative 2 here to integrate, all right? So we take the derivative, we get 1. Take the derivative again, you get 0. Awesome. If we get 0 in the derivative column, then that's great. We can stop there, right? Now what I want to do is I want to try and integrate this twice if I can. I don't know if that's going to be too tough or not, but I don't think it's going to be. So what we do is this. We take a look at this, and if we're going to integrate this, this is just power, kind of straight power, right? So let's add 1 and divide by that. So this is going to be x plus 3. We add 1 to the exponent, and then we divide by that. So that's going to be negative x plus 3 to the negative 1. So that goes here. All right? Negative x plus 3 to the negative 1. Okay, so now that we have that, really that's 1 over, right? And so this looks to me like a natural logarithm. So I can take the integral again, and that's going to be negative natural, oh, I should do that in red, shouldn't I? That's going to be negative of the natural logarithm of x plus 3. And this is just a 1 as a coefficient, so I don't have to undo any chain rule there. So we're just good. Now, this is awesome because this is now, I've fulfilled the third row of my DI table, and I can stop because I have a 0 over here. And so what we do then, if you recall, is you take, and I'll do a different color here, you take this term and multiply it by the term on the other column, second row, so one row down. So in green over here, the integral, okay, again we're finding the integral of this, should be x plus 5 over x plus 3, and that's going to be all negative there. Okay, so when I multiply those, then I'm going to subtract really 1 times the negative ln x plus 3. So that's going to be like adding ln of x plus 3 plus a constant. Okay, so that's what you get. Now I'm going to do the partial fraction method. That was pretty easy and straightforward. I'm going to do the partial fraction method, and then I'm going to show you one final thing here that is a little confusing, but I don't know. Depends where you're at with all this math stuff. Okay, so let's just keep this in mind. This is what we've got DI method. So partial fractions, I'm just going to put PF here, partial fractions. Now I don't know if you know this, but when we talk about this integrand, let me just get rid of this notation for a second. Now, partial fractions, the whole idea is that we can separate this into parts, okay, partial fractions of the whole here. So when you have a repeated factor in the denominator here, you can split this up as sort of one of those factors plus another constant over now both of those factors. And you just keep working your way up. If this is 3, then you do plus c over x plus 3 cubed and so on, and you keep going. We can stop here. So any rational function like this can be split up into partial fractions where you have a constant only on the top, and that is really cool. Why is that cool? Because this is easier to integrate when you just have a constant instead of when you have a whole other function here. So how do we do that? All right, so you get to this point, and you want to multiply by x plus 3 all squared, okay, to everything, and that gives us x plus 5 equals a times x plus 3 plus b, okay, when you multiply each term. All right, so now this is kind of cool. We're going to expand a little bit here. Ax plus 3a, and that's going to be plus that b over there. And what you're going to be able to do, this is kind of one level of taking a look at this, solving for a and b. If you look over here on the left side, we have a binomial with an x term, coefficient 1, and over on the right side I have one x term as well. I also have a constant term here, and really if a and b are constants, then 3a plus b is also one single constant, really, right? So this is how you find out these the coefficients here, or the constants a and b. Look at 1 equals a, because those terms have to be equal, right? So a is 1. Awesome. 3a, or 3 times 1, plus b from over here, has to equal 5. So b equals 2. Also awesome. Awesome, right? Can I get a amen? Okay, both awesome. You're agreeing with me? Okay, so a and b is 2. So what does that mean here now? Okay, let's go back and give me some room. Give me some space here. Okay, so I'll choose a color, like black. I know it's not really a color. So really I have now 1. So a is 1, right? A is 1. Let's just do this thing. A is 1. B is 2. Okay, that is awesome. So now if I go back to integral dx, this is now integral dx, integral dx. So this is going to be really easy to integrate these two parts, say partial fractions. And so what do we get? Let's just hope we get the same thing. So the integral of 1 over x plus 3 is ln of x plus 3. Technically, absolute value, but we won't worry about that right now. And then plus, now this one here, okay, so what do we do here? Well, if you take the integral, we did this already, right? That's going to be negative x plus 3 to the negative 1, and then of course times 2. So this is going to be plus, actually it's going to be plus and negative, so it's going to be minus 2 over x plus 3. Okay, hopefully you're with me. And then plus c. So this is what we get for the two different versions. Now this is the same as that. Yay. We appear to have a constant. Now are those equal? Don't know actually, because these are different. Now if you do this two different ways, and one of your classmate does this using partial fractions, you do this integration by parts, and you look and you say, oh, somebody is wrong. Well, actually, not necessarily. Not necessarily is someone wrong, because I want to take a look at this first one we did in green down here again. Do I want to look at that one? Yeah, sure, why not? So look at what happens here. This negative x plus 5, okay, this is actually x, we could say this is x plus 3, and then plus 2 in here, right, or minus 2 out here, right? So that's actually a minus, sorry, that's plus 2. So what this ends up to be is negative, right, x plus 3, and then a plus 2. Okay. This was 3, this was 5, 3 plus 2, okay, I put a 2 in there, that's a negative, so I need to put outside 2, okay, over x plus 3, all right? So what we have is I can split this up, can't I? And actually I'm going to put the negative, I'm going to leave that negative, whatever. And then here's the other part of it. You see this? Okay, so really, this also can be expressed as x plus 3. Let's leave the negative there, I guess. X plus 3. And then plus 2 over x plus 3. All right? So really, this is negative 1. Okay, so we have negative 1 plus 2 over x plus 3. Now this is almost virtually the same here, isn't it, except for the minus and the plus. But look what happens. This just kind of melts into this constant. Okay, and the constant, right? So we're getting closer here except for the negative, but that's how you can get, that's why you're both right. Okay, that's why you're both right. That's the whole point. That's my whole point there. Both these answers are the same. The constants are different. Okay, and you did this correct. So hopefully you can kind of see that. These two answers are the same. Okay, so you can decide which one you like. The DI method was maybe a bit easier to, a bit quicker and a bit simpler. But hey, partial fractions also good, and you can do it either way. So there you go. little verses there, partial fractions and DI method. Have fun.